Greetings everyone. This is about to be the beginning of a journey here in Astrophi. Feel free to grab a snack, let's venture into the cosmos. It's going to be the first video of a series about gravitational waves. Apologies to keep you waiting, here goes the first one. What are gravitational waves? On September 14, 2015, at 6 o'clock in the morning, scientists invented an entirely new way of observing the universe, something that no human had ever seen. Two black holes of 29 and 36 solar masses colliding, merging about 1.3 billion light years away. The collision sent ripples through the fabric of space-time, like the melts on a drum, and reached us and was detected by Laser Interferometer Gravitational Wave Observatory, or LIGO for short. The signal lasted for a fifth of a second, and it was detectors' first observation of gravitational waves. Well, it strikes the question as to what are gravitational waves, what causes it, and who proposed this idea? Well, for that, we first need to go into the basics. Gravity, the force that pulls any two objects together and can be applied on everything in the observable universe. The more mass something has, the stronger is its gravitational pull, and farther away the object, lower is its pull. We all might have heard about gravity in our high school, and how it follows the inverse square law. But what really are gravitational waves? If you're learning about this for the first time, it might be a bit difficult for you to understand, but bear with me. Gravitational waves are disturbances or ripples in space-time generated by accelerated masses and caused by some of the most violent and energetic processes in the universe that propagates as waves outward from their source at the speed of light. These were proposed by Henry Poincaré in 1905 and subsequently predicted in 1916 by Albert Einstein. When Einstein devised his general theory of relativity, he imagined gravity as a curve in a surface called space-time. A mass in space creates a depression in space-time. The bigger the mass, the deeper the depression, and the stronger the gravity. When the mass making the depression moves, that sends out ripples in space-time. These are gravitational waves. In other words, mass like a star, black hole, curves space and time. Isaac Newton thought of space and time as two separate things, but Einstein thought of space-time as a single thing, or more like a fabric of space-time. Einstein's mathematics showed that massive accelerating objects, such as neutron stars or black holes orbiting each other, would disrupt space-time in such a way that waves of undulating space-time would propagate in all directions away from the source. I know it might be difficult for you to believe, but these gravitational waves passes right through us. But this happens on a very minute scale that it's not possible for us to feel any of it. Scientists have built detectors that can detect them for us. That is the function of LIGO and Virgo detectors. We will cover more about how exactly they work in the next video. So once the detectors feel it, then what happens? Well, first, gravitational waves interact very weakly with matter. Unlike electromagnetic radiation, which can be bent, refracted, absorbed, or reflected, they travel through the universe virtually unimpeded, giving us a clear view of gravitational wave universe. The wave carry information about their origin that is free of distortion or alteration suffered by electromagnetic radiation as it traverses intergalactic space. Scientists can extract information about the wave's source. They can derive information like its mass and shape of its orbit. We can also hear gravitational waves by playing their signals through speakers. So two black holes colliding sound something like this. Scientists call this whistle or chirp. It's kind of the signature of any two objects orbiting each other. There are many examples of gravitational waves. Stars collapsing into a supernova, neutron stars colliding, black holes colliding, black hole devouring a star. As Dr. Michio Kaku put it, it's like a gravity telescope. Light telescopes allow us to see planets. With radio telescopes, we see galaxies. A gravity telescope opens up the possibility of getting baby pictures of the Big Bang, of getting inside the black hole to see what happens to the stars that falls in it. It can open up a whole new realm of astronomy. If you're still finding it a bit difficult to visualize it, take a look at this analogy explained by Dr. Michio Kaku. Think of throwing a rock in a pond. The impact creates waves, ripples, which begin to spread rapidly. The pond is empty space. Space-time. It's like a fabric, says Einstein. So when you drop a rock at the fabric of space-time, it causes ripples that travels at the speed of light. Einstein predicted it in 1916, but it took 100 years to finally prove that, yeah, bingo, Einstein was right after all. By now, this question may have come to your mind as why detect them? Well, LIGO has opened up a new window to the universe. Things like colliding black holes are utterly invisible to electromagnetic astronomers. To LIGO, such events are beacons in the vast cosmic sea. It increases our knowledge about the place that we currently live in, and it has opened up a new domain of astronomy. Each time a new telescope came online, it revolutionized understanding of the universe. I want to thank you so much for watching, and I'll see you here again in Astrophile. If you like the content, feel free to hit the subscribe button and press the bell icon so you never miss any upload.